Okay, so let us recall that in the last video we proved this result, namely that the set of all vector space homomorphisms from the vector space V into the vector space W itself is a vector space under appropriately defined addition and scalar multiplication, where V and W themselves are vector spaces over a common field F, and we proved that this set is also a vector space over that field. Now if you recall the proof, in the proof mainly what we did, we just verified all the vector space axioms one by one, and in only one of those, I won't say axioms, but we had to first of all make sure that this set is non-empty, and that we did by showing that there exists a zero vector here, which of course is the zero function from V into W, whose definition is this, which maps every element V of the domain space onto the zero element of that second space. Okay, we actually proved that this is an element in this, that is, this itself is a homomorphism from V into W. In none of the other axioms we state anything about some specific element being in this set. The only element, actual concrete element that we showed is always in this set is the zero element. So it may be the case that this space actually has just zero, namely this is the zero space consisting of a single vector. So you may be thinking that after doing so much work in showing that this is a vector space, we are just getting only one vector. If that is always the case, then of course our efforts went in vain, because then it will be an extremely boring space where nothing interesting could ever happen. But now the next result that we are going to prove will show that actually there are many other vectors. So let's see the next one, which is this theorem. This is theorem 431, and this one also is going to say something about this space itself, but now we know that it is a vector space. So the statement goes like this: if V and W are of dimensions m and n. R of dimensions means they are vector spaces. In this context, the things that we have been doing in this context, P and W are vector spaces. It need not be mentioned all the time. Okay, these are m and n respectively. Over F. So mentioning that this dimensions are over F also tells us that both the vector spaces are vector spaces over that common field F. Then our space of homomorphisms is of dimension mn over F. This is the statement. If V is m dimensional and W is n dimensional over F, then home V comma W is mn dimensional. So let's now see the proof. The author states that we are going to prove this statement by explicitly exhibiting one basis for this space that has mn elements, because that could tell us that the dimension is mn. So let us start off by choosing bases for V and W because they are given to be finite dimensional. The first one should have a basis with m vectors and the second one should have a basis with n vectors. So let V1, V2, etc. Vn be a basis of V over F and W1, W2, etc. through W1 be a basis of W over F. Now we somehow need mn number of objects here in home V comma W. That means mn number of vector space homomorphisms from V into W, which will form a basis for this space. So let's see what we can do. For indices I and j which vary like this, that is I and j are integers independent of each other and I can vary from 1 through m, j can vary from 1 through n. We define the function Tij from V into W as follows. Okay, so this will likely give us mn number of such linear transform, vector space homomorphisms. They are also called linear transformations. So let us now see how they are going to be defined. For any vector V belonging to V, there exist unique scalars say lambda 1, lambda 2, like that up to lambda m belonging to the common field, such that V is a linear combination of these basis vectors. Because this is a basis for V, we not only get these scalars but we get unique scalars. The uniqueness comes from the fact that the basis is a linearly independent set. Vm. Okay, we define Vtij to be equal to, this colon means its definition. Okay, this symbol is going to mean something, and that something now we are going to write. This is lambda I wj. Okay, so that's how we have defined the function Tij. Now let us first of all see whether what we have defined makes sense or not, whether Tij actually is a well-defined function from V into W. We have taken one input from the domain V, okay, For that input, we have got unique scalars that allow us to express V as a linear combination like this. Fine. Then our definition looks like this. So, looking at this output, lambda I Wj, we immediately notice one thing, that because Wj, whatever j is after all a vector in the second space W. So this scalar multiple of Wj, lambda I Wj is of course again a vector in W. So our output actually lies in W, in that space. Now what about uniqueness of this output? This output is unique because lambda I is uniquely determined by V. Once you choose V, there exist unique scalars. So it does not matter what I is, lambda I is going to be unique. So that's why this output is also unique. And that is why Tij is well defined. So instead of saying all these things, we just simply write clearly, because these things are also easy to see. Clearly, Tij is well defined. Actually, we are saying this for all the variations of I and j at once. Okay, but we are not going to mention that. If you want, you can choose to really show why this is well defined. In fact, it is advisable to do that for the first few times so that the things stick in our brain, and then after gaining experience, you yourself will realize when you can leave out some information from a proof. There is no hard and fast rule, but you will realize from experience. So Tij is well defined. Okay, now the next thing we want to show is that these Tijs actually are homomorphisms from V into W. So for that, we take, say, another vector V prime in V. Then for this also there exist unique scalars. And to maintain uniformity, let me take lambda 1 prime. It's not necessary, but it looks nice and it's easier to keep track of things this way, such that V prime is lambda 1 prime V1 plus etc. plus lambda m prime V n. Okay, now we are going to apply Tij on V plus V prime. V plus V prime. In an attempt to prove that Tij respects vector addition. Okay, so we are going to calculate this. Looking at the expressions for V and V prime as linear combinations of basis elements and using the vector space axioms that we have in our domain space V, this V plus V prime can of course be written like this. Prime V1 etc. plus okay, let me write it there. on this we are applying Tij. Keep in mind that this expression that we are getting, this one for v plus v prime, to get to this we had to use many of the things that are true in v. For example, we have used the fact that v is an abelian group with respect to addition. So you can write the terms in any manner you want, write the vectors, and then we have used one of the 4 vector space axioms in taking v1 common out and write lambda 1 v1 plus lambda 1 prime v1 like this. That's what we did here basically. So now we apply the definition of Tij. So this becomes, so we are going to take the ith coefficient, ith scalar, that is lambda I plus lambda I prime wj. So we have just simply applied this definition here. Now whatever axiom we said we used here, that same thing is also true in the second space w. So in place of this we can write lambda I wj plus lambda I prime wj, and this thing is simply v, the Tij image of v, and this is the Tij image of v prime. So Tij actually does respect vector addition. Now next we look at scalar multiplication. Also for, let's take some scalar alpha belonging to f. Another such calculation will now be carried out. Alpha v Tij. Alpha v from the expression of v as a linear combination of basis vectors can be easily seen to be equal to this. Vm t we are doing calculations on vector spaces and we are short of space here. Alpha 1, oh sorry, that is lambda. Okay, so I think I was writing something wrong. Alpha lambda 1, am I doing it correctly? Alpha lambda, yes, alpha lambda 1 v1 plus alpha lambda 2 v2 and like that to alpha lambda m vm. Tij. To get this expression from this, of course we had to use some such vector space axioms. Okay, you understand what we did here. Now again applying the definition of this function, we get alpha lambda I wj, and this of course equals alpha times lambda I wj, which is one of the axioms in the space w. And this thing inside the brackets is your v Tij. So Tij respects not only vector addition but scalar multiplication. Hence Tij itself is actually a vector space homomorphism. In other words, it's an element of this space for all I and j, for those variations of I and j which we are not going to mention. Okay, we now show that the set of these functions is a basis for whom v comma w over f. So we are required to show two things. One is that this set spans the space, and the second thing is that this set is linearly independent. Over f. Right. So let us now first of all show that this set spans this space. For that we are going to, of course, do what? We are going to take any element here and show that that element is a linear combination of these Tij's with with using some appropriate scalars from the field F. So let S belong to any, S be any element in this space for each I varying from 1 through m. There exist unique scalars alpha I1, alpha I2, etc. up to alpha In. These are double indices belonging to F such that Vis is equal to alpha I1 W1 plus alpha I2 W2, like that it goes, and the last term is alpha In Wn. You understand why we need double indices here? That is because this first index I denotes the fact that this is the expansion for, the expression for Vis. It's the image of Vi under S, and being the image of Vi, which is a vector in capital V under S, and S is the function from V to W. This thing is of course in W, so it is expressible as a linear combination of the basis vectors in W, which are these Wj's, W1, W2 up to Wn. And the second index, of course, keeps track of whose coefficient this thing is. This alpha I1 is the coefficient of W1, so we have 1 here. For N we have N here. For J we have J there. Right. So now consider the element. We are going to now write a long element. Long means I am going to make the expression long for the sake of clarity. So now we are going to write something which is going to be a linear combination of these Tij's with scalars that are coming from here, these expressions, and that thing precisely is this: alpha 11 T11 plus alpha 12 T12 plus alpha 13 T13, like that it goes. Alpha 1 N T1N, but it's not over, it continues. Let me continue from there. We are going to use all the alpha ij's available here, and we are also going to bring in all the Tij's. So after that, plus, so let me write we cannot say the next set of things, but in this particular order that I am using here, I say next alpha 12 T12 plus alpha 22 T22, like that it goes up to alpha 2N T2N plus, and then it goes like this. Let me write a general one also somewhere in the middle: alpha I1 Ti1, etc. plus, unlike these sums, here I am going to write a still more general one, which is absolutely general: alpha ij Tij plus alpha in Tin. These many terms I am writing simply for the sake of showing how things are going here. And finally, of course, we have alpha M1 Tm1, etc. plus alpha Mn Tmn. This entire linear combination of the Tij's with this particular scalars can of course be more compactly written like this: alpha ij Tij, where I cannot write like this at once, no? Because M and N may be different. This, which looks like an abstract symbol. It is much less clear than this, but you understand what this thing is. Now our aim is to show that actually this T is equal to S. So that way what we will achieve is this: if we can show that S is equal to T, then S becomes a linear combination of the Tij's, and that's what we want. So now we are going to show that. Now to show that S is equal to T, of course, because they are functions, we just have to show that they give us identical outputs for the same input. And since the outputs for S are already available on the basis vectors for V, so it's enough to look at the effect of T on these basis vectors only. Do you see why? So what I am saying here is that if I manage to show that VIS is equal to VIT for all I, then that automatically implies S is equal to T. Why is that so? Do I not need to show that the same is true in fact for all the vectors V in capital V? Yes, of course I need to show that, but this thing implies that. Why is that so? That is because every vector in capital V is a linear combination of these VI's. So if I manage to show that S and T behave identically on the basis, then that automatically implies that it also behaves identically on the entirety of V. And in concluding that thing plays the role that this S and T are actually linear transformations or homomorphisms, because if you, for example, have a general vector V which is a linear combination like this, so applying T on V is the same as applying T on the basis vectors and then combining things like this. So if you show that this V1T is equal to V1S, V2T is equal to V2S, all the way up to VMT is equal to VMS, then you have S here in place of T, and then you can go in the other direction, and that thing ultimately will be equal to Vs. So you will end up proving that Vt is equal to Vs. So that's why it's enough to show just this. Okay, now we go to the actual task of showing it. For, we can continue from here itself now. For any I satisfying these inequalities, we will need this expression. Now when I am going to apply T on Vi, I of course won't be using this, I don't want to say I won't be using the entire expression, but I won't write this many terms, just the things that we would need. Vit, let me write like this, I will need space. Vit is equal to Vi. Let us first write this thing. Alpha 1 1 T 1 1 alpha 1 n T 1 n. If you want, you can write the second terms also, okay, in these parts of the entire sum for your own clarity. I chose to not write, say for example, alpha 1 to T 1 2 because it will take much more space. So this plus this part, there is no need to write. Okay, it's there, we understand it, but we are of course going to write this I part because we have I here. Ti1 alpha in Tin plus, and then of course it goes like this. Okay, so here the input is just Vi and the function that you are applying on it is a gigantic thing like this. Anyway, now this thing is equal to Oh, I said I will need this, no? Let me write it somewhere else, because I cannot just simply stop here. We have VIS is equal to alpha I1 W1 alpha I2 W2 like that up to alpha IN WN. We need this because we need to see that ultimately whatever we end up with here after the calculation is over is actually equal to this expression. So that way we will recognize this as VIS. Okay. What did we do in this step, by the way? We have not used any, the fact that these Tij's are homomorphisms or linear transformations here in this step. All we did here is we applied the definition of this expression. Keep in mind that this expression itself is a linear combination in our home space. And by the definition of addition and scalar multiplication in this space, we have got this step. We have just used the definition of addition and scalar multiplication in this space to come from this to this. Okay. Now we are going to see what these images are. For example, VIT11, where because we have separately written these I things, so that means we want to mean specifically that I is not equal to 1. Okay, now let us think for a moment what VIT11 should be according to definition, because we just have to apply the definition. How to calculate VIT11? What was the definition of VT11? Originally we had V like this, no? Lambda 1 V1 etc. plus lambda m Vm. Our definition for VT11 should be this: lambda 1 W1. This one is coming from here and this one is coming from here. Now what about Vi? Vi itself is also a linear combination of the basis vectors V, all the V's, and specifically that linear combination in this case is this. That means the coefficients of all the Vj's are equal to 0 except j equal to I, where the coefficient is 1, and because such a linear combination is unique, so this is the only such linear combination. So from this expression and the definition of T11, we then get the fact that this thing is equal to the coefficient of Vi, which is 1 times lambda, W1, which is nothing but W1. Okay. Oh, what? Okay. What the hell did I say here? No. What I said now is wrong. This thing is not the thing. This is okay, but because our so we need to fine. I also got confused. See how easily we get confused with these things. T11 V1 should be the first coefficient times W1. Here the first coefficient is 0 times W1 is 0. Okay. And the same thing is true for these other images here in the first part of this sum. You will realize when you calculate the things, did I again make a mistake? I think I wrote something wrong here. Or, oh, I did not finish writing the sum. I brought the thing down here, I brought it from there to here, and I forgot to finish the sum. Alpha mn vitmn. Analyzing the situation like this, you will realize this thing. Let me use something else. Okay, T alpha beta is equal to we don't have lambda. Alpha, that is, it is non-zero if and only if non-zero if and only if I is equal to alpha, and the appropriate coefficient times w beta will be there, and it is 0 just like this case if and only if I is not equal to alpha. So what I am trying to say here is that only this part of the sum gives you something. The other things will give you the zero vector in W. So I myself got quite confused here, but anyway, the confusion is not something fatal. So we have got this. So that means only this part of the sum survives, and we have alpha I1. This one will be what? W1. Actually 1 W1, but that is of course W1. And then alpha I2 W2, and it will go like this up to alpha IN WN, which is equal to, yeah, that's why we needed this. You see, alpha I1 W1 plus alpha I2 W2, etc. up to alpha IN W1. So that thing is equal to VIS. So VIT is equal to VIS for all the all the possible values of I. Hence, S is equal to T. That is, without being too specific, the Tij's span our home space. So this is one half of the proof. Now we need to prove that the Tij's are linearly independent. Why am I even carrying this? Next, let beta 1 n beta 1 towards 2 1 2n Mn belong to F. Let this be some scalars. To show that the Tij's are linearly independent, again we have to consider some linear combination of them and set that linear combination equal to 0. Then we have to prove that all the scalars are 0. So that's why we consider these scalars such that this linear combination beta 1 1 T11, again another such sum 1n T1n plus let us just write this one also 2 1 T2 1 beta m1 Tm1 plus beta mn Tmn is equal to 0, and this 0 is of course the 0 linear transformation. Because I got confused at the end of this calculation, and sometimes I get confused in some places, you may have already seen. I urge you to go through these things carefully, and if you spot even a small mistake, please let me know in the comments. Okay, this will become very helpful for me. Now we need to prove that all these beta ij's are equal to 0. So this is a linear combination of some elements in v comma w. After all, this is also a function from v into w. So we can apply it on any vector in capital V, in particular on the basis vectors. So for any I lying between 1 and m, we have Vi Actually, this type of small hiccups and confusions are supposed to be not there in a video, because things are usually edited out, but I don't like editing things. You need to see how I am struggling. Plus beta 1n T1n plus beta 21 T21 plus beta 2n T2n So applying this thing on Vi is the same as applying the zero function on Vi, which will give us, of course, 0. That is, let us continue the calculation like this, because we are not writing this as an equation array. So this thing implies, now we are going to apply things, because we have already seen what happens when we apply such a linear combination of the Tij's to Vi. So now we need not write everything. We are just simply going to write the things that has I here as the first of the double indices. Beta I1 ti1 plus beta in tin, because the other part will give us 0. This is equal to 0, that is beta i1 vi ti1 will be w1, vi ti2 will be w2, and it will go like this. Finally beta in w1 is equal to 0. But note that now this is a linear combination of the basis vectors, the w's, in the space capital W. So the basis vectors in capital W are like any basis is, they are linearly independent, since these vectors are linearly independent all the betas are equal to 0. Now this is for some arbitrary but fixed I. Now if you vary the I like this also, then you capture all the beta ij's. So beta ij is equal to 0 for all i's and all j's. Hence the Tij's are linearly independent. This shows that the dimension of our space of homomorphisms is Mn. The proof is over, but there is a question. We have shown that the set of Tij's is linearly independent and it spans the space, so it's the basis for our space. So the number of elements in it should be the dimension of the space by definition of dimension. However, how do we know that there are Mn elements? For that we need to we should have shown that the Tij's are all distinct, that no two Tij's where at least one I or j is different are equal. Do we need to really show that separately? Actually, we don't need to show that, because if you list the Tij's in any order, whatever order you choose to write them in, the fact that you have shown that they are linearly independent itself implies that they are distinct, because if in that list there is some repetition, then they cannot be linearly independent. It's like having something like this. Say these are 4 vectors where there is a repetition. So what you do, you consider this linear combination. And this linear combination of course will be 0 in spite of the fact that two scalars are non-zero. So this list cannot give you a linearly, a collection of linearly independent vectors. They are linearly dependent. So the fact that you have shown that the Tij's are linearly independent automatically tells you that there is in fact no such repetition, and that's why the Tij's are distinct, and as a result there are mn number of Tij's, and that is why the dimension is mn. Okay. Now what does this have to do with home v comma w having some vector other than the zero vector, which is what we are coming to next. A consequence of the above theorem is that if our original spaces with which we started, they are non-trivial spaces, that is, they themselves are not zero-dimensional spaces, they have dimensions higher than 0. If this and are finite dimensional, say over some common field F, then our space of transformations itself is a non-zero vector space. That means there is at least one non-trivial linear transformation or homomorphism from V into W, since dimension of this space is equal to the product of the dimensions of these spaces, which is what we proved here. And each one of them is greater than 0, that is greater than or equal to 1. So their product is also greater than or equal to 1. So that way we know that if we start off with non-trivial vector spaces, then there are also non-trivial linear transformations from any one of them to the other. Now this result of course has two special cases which are of importance. They are corollaries. First we have corollary 1. If V is a vector space over F whose dimension over F is M, it's finite dimensional, then the dimension of this space where both the spaces, I mean V and W, they are the same thing, V over F is m squared. And this space will occupy our time towards the end of this book. And a detailed study of this space is what we call linear algebra. Its elements are operators, and in another representation we will see these things. Actually, this vector space is isomorphic to another familiar vector space, the vector space of m by m matrices over F, under matrix addition as vector addition and multiplication of a matrix by a field element as scalar multiplication. So this is one thing. And then we have corollary 2. If again V is a finite dimensional vector space over F, then the dimension of this other possibility, where the first space is V and the second space is the one-dimensional space F itself, is m times 1, which is m. There are proofs of these corollaries, but which are so they follow so easily from the theorem that we proved today that I am not going to supply the details. This is equal to m. I will just simply mention one fact that will be used in proving this thing. Namely, I just write like this: note that the dimension of F over F is 1. Any field is a vector space over itself in a trivial manner, and in that space you take any single non-zero field element, say you take alpha. This itself is a basis. If you ask why, it's very easy to show why. Any beta belonging to F is a linear combination of this alpha. How? You can write beta as beta alpha inverse alpha, where beta alpha inverse is a scalar because it is in F. Keep in mind, we chose alpha to be non-zero. So alpha inverse exists in F. So beta alpha inverse is interpreted as a scalar. Where am I taking it? As a scalar, and alpha is treated as a vector because F itself gives us the scalars and this also gives us the vectors. So you have expressed beta as a linear combination of the basis vectors. We did not show that it's a basis, but of this set where there is only one vector, so it just simply is a multiple of that vector. So that means this spans F. And is this linearly independent? It is, because it has only one non-zero vector, that's why it is linearly independent. If you take any gamma from F, which is treated as a scalar, and you consider this scalar multiple of alpha by gamma, and you set this thing equal to 0, then because alpha is non-zero, gamma has to be equal to 0. And that comes from the fact that if you choose gamma to be non-zero, then you can multiply on both sides by gamma inverse, giving you alpha equal to 0, which will contradict this thing. So that's why this is linearly independent, this spans F, so this is a basis for F. And because this set is a singleton set, so the dimension is 1. And before we end things, though, there is a small discussion about this second possibility. Note that this corollary tells us what, this second corollary. It tells us that the space V and the space V comma F actually have the same dimension when V is finite dimensional. And we know from a previous result that two finite dimensional vector spaces which have the same dimension are in fact isomorphic. So that's why when V is finite dimensional, V is isomorphic to this space. However, the author says that this isomorphism has shortcomings. When V is not finite dimensional, no such nice isomorphism exists. And in fact, in general also, there is no general construction that will actually give you an isomorphism from V into this. However, we will show at one point that there in fact is an isomorphism from V into this somewhat more intimidating looking thing, which takes us one step further. This space is known as the space of linear functionals on V. Linear functionals are treated as linear transformations whose inputs are vectors and outputs are scalars. It is also called the dual space of V and is sometimes written like this, V hat. There are other notations also, and this is the double dual. Although the original space and the dual are isomorphic when the original space is finite dimensional, but there is no nice isomorphism that can be generally constructed. It just simply is a consequence of the fact that these two have the same dimension when they are finite dimensional, that we are having this fact that they are isomorphic. However, there is a general construction where we will construct an isomorphism between a vector space and its double dual. We will do these things, okay, in the next update, in the next video on vector spaces. But I end things here for tonight. If you want to say something positive or negative, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. So with this, I just finished things for tonight. The next video, of course, will be on Friday. So we have gone through again, because we are going through things cyclically. No? First we saw group theory, and then we saw fields, where that splitting field thing we did, and now we have seen vector spaces. So this Friday, let us go back to calculus, and then we will follow that up with our usual number theory, graph theory, and then again things will cycle back. So that's just it. I wrap things up. So see you on Friday with somewhat lighter things on calculus. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.